Hi everyone, I'm Dr. Surjit Singh. Today I'll talk about the Leetcode problem, maximum stones removed with common row or column. Let us begin. We are given a number of stones and their coordinates. If a pair of stones lies on the same horizontal or vertical line, then we can remove one of the stones. We are to find the maximum number of stones that can be removed. Let us discuss the DFS approach. We begin by setting up a graph of stones. Connected stones share a horizontal or a vertical line. We will then find set of connected component of stones. All but one stone can be removed from the set. Last stone will not have any pair and cannot be removed. So we will proceed to find number of connected components present in the graph using DFS. There are 6 stones numbered 0 to 5. We are given their coordinates. Each stone will become a node in the graph. Their graph looks like this. The pair of stones connected by a vertical or a horizontal line are adjacent. Before we define the DFS function, let us set up the edge list for the graph. We use a double loop to cover all the pairs of stones. In the first iteration, stones 0 and 1 form a pair. The function r adjacent is true for 0 and 1 because their x coordinate is same. So we record the edge between them. The edge is non-directional, so we save both 0 to 1 and 1 to 0. Stones 0 to are also connected. This gives two more entries in the edge list. But 0 and 3 are not connected as they do not have a common coordinate. 0, 4 gives another pair of entries. We continue in the same way, and this is our final edge list. We initialize the visited list for all stones as false and initialize the number of connected components to 0. We start a loop to process all the stones which are not already visited. We increase the number of connected components by 1. All the stones that can be reached from 0 directly or indirectly form one component. To find it, we start DFS with 0. We mark the current stone as visited and iterate over its adjacent stones by calling DFS for stones that are not already visited. First edge of 0 is 1, so we again call DFS with parameter 1 and mark it as visited. The only neighbor of 1 is 0, which is already visited, and the call ends. Next edge of 0 is 2. We mark this also as visited. 3 and 4 are the edges of 2 that are not visited. We first call 3 and mark this also as visited. 3 does not have an unvisited neighbor, so this call ends. The last neighbor of 2 is 4. We mark this also as visited. Call for 2 ends. Call for 0 also ends. Coming back to the loop over I, stones 1, 2, 3 and 4 are already visited. 5 is not part of the old component. For I is equal to 5, we increase the connected components further by 1 and call DFS for 5, in which we mark 5 as visited and the call ends. Loop over I ends and 2 is the final number of components. 5 is a separate component not connected with any other stone, so this cannot be removed. In the other component, there are 5 stones connected to each other. 4 of these can be removed. The last one will not be connected with any other stone, so the number of stones that cannot be removed is equal to the number of components. Hence 4 is the number of stones that can be removed. Building of graph requires a pair of loops for which the time complexity is of the order of n squared. In DFS, all nodes are processed once, So the total time complexity is of the order of n squared plus e, where e is the number of edges. If all the stones are on x-axis, E is maximum and its value is of the order of n squared, while if all the stones are on the diagonal line, E is 0. So the maximum time complexity is of the order of n squared. Adjacency list takes OE space, visited set takes ON space. Total space complexity is of the order of n plus E. However, maximum E is of the order of n squared, so in the worst case, space complexity is of the order of n squared. In this method, we will now use a different form of the graph that makes its processing linear. Both x and y coordinates can have 10,001 integral values between 0 and 10,000. So we define k as 10,001. The graph this time has two k nodes. First k node numbers are for the x coordinate values and the next k nodes for the y coordinates. Each node has an edge list. We are using magenta color to indicate that k is to be added to the values that are for y coordinates. 2 in magenta color means its value is k plus 2. We process all the stones to set up the graph. Consider the first stone with coordinates 0, 0. Hence, edge list of node 0 will store k as its adjacent node. Note that magenta 0 is considered as k plus 0, which is k. As the graph is non-directional, edge list of node k will also store node 0 as its adjacent node. Next stone has coordinates 0, 1. This means that node 0 is adjacent to node k plus 1 and node k plus 1 is adjacent to 0. Next stone is at 1, 0. It means node 1 is adjacent to node k and vice versa. Stones at coordinates 1, 2, 2, 0 and finally at 3, 3 give these entries in the edge list. This structure of graph will work because we are only interested in finding the number of connected components. We initialize the visited list to false for all the nodes and initialize number of connected components to 0. Like before, we process all the nodes that are not visited and for which edge list is not empty. We increase connected components by 1 and call DFS. DFS function is same, however, stones are not the nodes this time, the coordinate values are the nodes. All adjacent nodes in DFS are marked as visited. Adjacent node of 0 is k. It is marked as visited. First neighbor of k is already visited. Its next neighbor is 1. This is also marked as visited. Neighbor of 1 is k plus 2. 2 DFS calls end. Next neighbor of k is 2. 2 more DFS end. Next neighbor of 0 is k plus 1. All DFS calls end. In our loop over I, the next node which is not visited is 3. We increase connected components by 1 and mark node 3 as visited. Its neighbor is also marked as visited and all calls end. And the number of components become 2. And final value of result is 4. Building of the graph takes O(n) time. In DFS, each node is processed once and there are 2k nodes. As k is far greater than n, time complexity is of the order of k. Edge list has 2k components, but we will fill up entries of the order of n only. However, visited list takes space of the order of 2k, so the overall space complexity is of the order of k. Thank you for your time. Next week, I'll talk about the second part of the same problem. Please stay tuned.